So our final section of this chapter gets us into this whole structure of aromatic or aromaticity, and then we'll just briefly talk about a couple reactions that aromatic rings can undergo. So up until now, we've defined an aromatic ring, or the aromatic functional group, as being this six-membered ring containing alternating single and double bonds. And further, we said that we can represent it like that, or we can represent it in this way. Now, as it turns out, neither one of these is exactly what an aromatic ring is. An aromatic ring ends up being a hybrid of these two. And in many cases, we can represent that like this, showing that the electrons of the double bonds, being these, that's 6 total electrons. And what we're saying is that those 6 total electrons are actually delocalized throughout the entire aromatic ring. And anytime we can share electrons, we can spread out electrons, that's something that's very, very stabilizing for a molecule. Now, it turns out that this isn't the only situation that qualifies as aromatic. There are many others. This is by far the most common. But there will be times later on in this course in biochemistry where we see other groups that we also classify as aromatic. And we won't get into that in much detail here, but it's just something to sort of keep our eyes open for down the road. All right, so what can we actually do with aromatic rings? How do they react? Because given that we've said now a couple times that aromatic rings are not alkenes, that means they're going to react differently. And the primary issue is that they're just not as strong in terms of how reactive they are, not as good of a reactant. We're not getting into what we call the reaction mechanisms in this course. Reaction mechanisms are the step-by-step pathway by which a reaction occurs. And we draw arrows that show the flow of electrons through a reaction. And a mechanism actually helps us to see where bonds break and where bonds form within a reaction. That's not something we're going to do here. But the main issue is that in order for an alkene to react, in almost every case, the alkene gives its electrons to something. And because an aromatic ring is so much more stable, it's not able to give its electrons up as easily. And so when you're dealing with a situation where you have something that's not very reactive, you have basically two possibilities. Those two possibilities are you can either make your starting material more reactive, or you can make the reagents more reactive. And so with reactions of aromatics, it's the reagents that we make more reactive. So you may recall that we said previously that an aromatic ring won't react under the same conditions that an alkene will. And that's because the bromine as a reagent is not strong enough. It's not reactive enough. So if you want to get your aromatic ring to react with bromine, you need to do it a little bit differently. And not only do you need to do it a little bit differently, the entire reaction ends up working a little bit differently. So if you recall, when we did bromine with an alkene, the alkene went away and we got two bromines where the alkene was. We don't get anything like that with an aromatic ring. And again, that's largely due to the stability. That aromatic ring is very, very stable, and so it doesn't want to go away. And if we got rid of the alkene, or one of those, if we got rid of one of those, then our product would be a lot less stable. So what we need to add here for this reaction to take place is something like iron bromide. Now there are other substances you can use as well, but the purpose of iron bromide is it functions as an acid. And clearly you can tell it can't be a Bronsted-Lowry acid. It can't be a Bronsted-Lowry acid here because it doesn't have any hydrogens. So it's functioning as a Lewis acid. But what occurs is before your aromatic ring can do anything, the bromine and the Lewis acid react, and they form an intermediate that behaves as if it's Br+. The reason I put it in quotes is it's not actually Br+, but it acts like it is. And as a result, the aromatic ring is able to react, and one of the hydrogens on the aromatic ring gets replaced by a bromine. And so we can do this reaction with bromine, and we can do it with chlorine as well. So same thing, Cl2, FeCl3. And again, you'll replace one of the hydrogens on the ring with a chlorine. Can't do this with iodine. Iodine, it turns out, is not reactive enough. And you also can't do it with fluorine. Fluorine is actually too reactive. And so there are other ways to put iodine and fluorine onto an aromatic ring, but we're not really going to worry about those in this course. All right, what else could we do with an aromatic ring? Well, we could put a nitro group on, NO2. And we do that by using nitric acid, sulfuric acid, and then you notice I'm putting this uppercase delta here. And what that uppercase delta means is that we're heating the reaction up until it boils and leaving them there. But as a result, this reaction replaces one of the hydrogens on the aromatic ring with a nitro group. Now, nitro groups by themselves aren't that useful, but it's actually really, really easy using something like hydrogenation. Same conditions, same reagents we saw for hydrogenating an alkene. Or we can use something like tin chloride and acid, and that converts our nitro group into an amine. And amines are, of course, very, very important functional groups in many different contexts. All right, our last reaction for aromatics is the sulfonylation reaction. The conditions for sulfonylation are actually very similar to nitration, except we don't use the nitric acid, we just heat it up with sulfuric acid. As a result, we end up with this SO3H group on our aromatic ring, which has two fairly important purposes. One is these types of sulfur groups have traditionally been very useful for making a class of molecules known as sulfa drugs. Sulfa drugs are antibiotics which are not used to the extent that they used to be. It was found out over time there's a lot of people that have allergies to sulfa drugs, and so they're not always the most useful, but they still get used, and this is one of the reactions that you need to make them. In addition, if you remove this hydrogen and make a sodium salt, then depending on what else is substituted on your aromatic ring, this is how a number of common detergents are made. Alright, so that's actually it for this chapter, and from here you should do the reactions of aromatic compounds practice, and we'll go over those in the next video.